So now it's my pleasure to introduce to you Dan Stowell, who is Associate Professor of AI and Biodiversity at Tilburg University. He's also at the Naturalis Biodiversity Center and the GADS in the Netherlands. Dan works on how machine learning and computational methods can help us understand animal sounds and monitor biodiversity through large-scale sound analysis. He's also contributing to climate action through Open Climate Fix and OpenStreetMap, using AI to support solar panel mapping and environmental sustainability. With this said, I will hand over the word to you.
Okay. Thank you very much. Thank you for the kind invitation, and thank you for the introduction. I'm really excited to be here today because I think this is a really good, stimulating gathering. I'm looking forward to the rest of today. I am particularly grateful to Oisin, who has introduced quite a lot of the context for what I'm going to talk about. So, of course, he's spoken about biodiversity mapping, and I am also going to be talking about biodiversity mapping as my target, as my goal. Let's see. So I will start with the big picture that I'm sure you know the IPCC. You may also know the IPBES, International Panel on Biodiversity and Ecosystem Services. That's the equivalent for biodiversity of the IPCC. Now, they got together in 2021 and mapped out the relations between climate change and biodiversity, and their report is really useful because it actually points out that there is so much common cause between biodiversity and climate change. They share direct drivers, they interact with each other, and of course they both affect human quality of life. A little bit more detail about that came out in the IPBES Nexus report very recently, which these graphs are just indicative here, but they put a lot more detail onto that. And so they did some scenario modeling. They found that a balanced scenario in which we work on climate, biodiversity, and economic goals together actually has the best outcome, the best balanced outcome overall. So these reports are really great for setting the big picture of what we want to achieve here. So I'm going to be talking about biodiversity. I will also say a little bit about climate. But you know, the common cause is not just a nice idea here. It's really the point. Here's another biodiversity map for you. This is the map of all of the insect observations in GBIF, this global pooling that Oisin also mentioned, and for the whole of the 21st century so far. And what you can see from this is that the monitoring data is biased. According to this map, Europe is the place to go if, oops, excuse me, I've pressed the wrong button here. Europe is the place to go if you want to find insects. And with mosquito season approaching, maybe you agree, but no, this is very biased. And as well as improving the modeling of where we expect things to appear, we also really need efficient ways to monitor animals at very large scale. And that's why I want to emphasize the global perspective here. So I work at Naturalis, which is the Biodiversity Center for the Netherlands, and also Tilburg University. And here is some of my team here, fantastic people, mostly postdocs and PhD students working on these topics. And let me just tell you a little bit about what we do. So I'm going to give you 3 postcards of the projects that we run. The first one is, well, it's actually a cluster of projects, Garden, Mambo and Tetris, in which we are using deep learning to identify species from sounds and from images. And this is one of the kind of headline tasks in all of this work. It's very common to attempt this, right? So we have sounds, we have images. What is the species? So this is the headline thing that we've been working on for many years, and there's still plenty of work in that. So in these projects, we are trying to build systems to perform species classification as a service for Europe. More recently, we've launched a network, a doctoral network called Bioacoustic AI, and so this is 10 PhD projects. Here I've shown the 3 PhD projects related to me, and we're digging into some more detailed topics within that. So, for example, other recognition tasks as well as species, or to try and work out what to do when there are unknown species and unknown sounds in the data. And the third one, a project called TabMon, which is about bird acoustic monitoring across a wide geographic range. This logo here in the middle is not just a logo, it's also a map of where our monitoring sites are. So it's led by a Norwegian team at the NINA Institute, and we have acoustic monitoring the length of Norway through the Netherlands down into France and Spain. And so the challenge there is that we have real-time acoustic data streaming in, and yes, we can perform identification of sounds that we hear, but how can we do that reliably, robustly, and try to mitigate the biases in this system and adapt to the very different conditions in our different acoustic monitoring sites? So part of the strategy there, which Ben McEwen works on with me, is a kind of human-in-the-loop process where we try to make use of a very small amount of human expertise to try and improve this. So these are the kind of projects that we work on. And for today's talk, I actually want to focus on something slightly different, which is what about AI's carbon footprint itself? Now, this can be a hot topic, and we might have some arguments about it at some point during the day, but of course there are headlines, just a couple of headlines I put here. I will start by plugging a really nice paper from last year, which is not from me at all. It's from a real dream team of authors: Gail Varroquois of Scikit-learn fame, Alexandra Lucioni, who started some of the early AI footprint work, and Meredith Whittaker of Signal fame. That's a fantastic team. And it's a really nice paper which sets a kind of position paper for how the field of AI should proceed, given the potential negative impacts on climate. So I definitely recommend that. And I want to sort of zoom in a little bit on how does this affect the viability and the strategy for AI for nature. So, the problem statement. If we really want to monitor biodiversity at scale, and I'm thinking here of monitoring it with sounds, but maybe also images, we need very large-scale sensing, and we need lots of inference. So if we just naively rolled that out, that could be potentially a very large carbon footprint, not to mention e-waste and other side effects. This is a problem that we haven't fully faced up to. We have ambitions, many research groups. So at Naturalis, we have the ambition almost formally to monitor all species as a service for the Netherlands, and then as part of our EU project to monitor all species for the whole of the EU. We're not the only people with ambitions to do this at global scale. So we actually need to sort of take stock of where is it that we're trying to head, and are we heading there in the right way? So what I want to do now is I'll talk about the footprint of AI in this particular context, and I'm going to break it into 3 parts. So training, hardware, and in use. Training the algorithm, the hardware that includes embodied emissions, and then in use. So I'm going to use the word inference, which is what we often say in machine learning for the process of taking a deep learning algorithm and applying it to some data in practice. And I'm mostly focusing on carbon emissions here, though of course there might be other side effects. Okay, let's go. So, number 1, I'm going to bring some good news, by the way. Some good news that is like maybe even things that you already know. There's one thing about training neural networks, which is actually, it's a good news that has gone unnoticed. Pre-trained networks. So what that means is, lots of neural networks have already been trained in the past. And it's now very common practice not to start from scratch in training your own network, but using the effort that has already been expended in training a network. I'm not telling you anything new here, because this is widespread practice in machine learning now. But it actually has a great impact because it means that we can very often train neural networks in much shorter time and with much shorter carbon footprint. So even if the neural network is large, in recent years, the impact of training it has gone down a lot. Two methods for reusing a pre-trained network. The most common one is called fine-tuning. And so fine-tuning here is simply, here is my neural network, which has audio as the input. Here are some layers, and then we predict a class label. And let's say the basic way of reusing this trained neural network is to take all of the layers, but actually I'm going to chop one layer off. And what comes out of this penultimate layer is some kind of representation. And now I'm going to train new layers to make use of that, to predict other things such as, well, other attributes. So fine-tuning is basically just reusing the neural network. The second method for reusing a pre-trained neural network is something called model distillation. And now in that one, I take my pre-trained network, and now instead of reusing it directly, I want to train a brand new neural network. So I am training it from scratch, at least potentially, but I am training it not to predict some ground truth that I've collected. I'm training it to make the same predictions as this big neural network would make. That might seem a bit strange and indirect. One of the really nice advantages of it over the fine-tuning method is that this green neural network here can be anything I like. So I can replace the big old-fashioned blue network with my new fancy green network. And so in this recent work, we've compared these strategies. We made some other comparisons as well. And this is for bird species classification for European birds. There are a few different things on this plot. I will tell you that in the first column, we have some transformer-based models and some CNN-based models. The pre-training might be from bird data or from general audio data, but the transfer method is what I've just been talking about. We're either doing knowledge distillation or fine-tuning. And you can see the performance scores here. Actually, this violin plot shows the performance scores. So we've got multiple different methods here. And okay, so the highest performing method is using bird audio as the pre-training source. Okay, and using knowledge distillation as the method. If you look at these violin plots here, though, the violin shows the performance per species. So actually we see quite a large variation per species in how well a system does. And you can also see that these violins are quite large, so there's a lot of overlap between the systems. If we're looking for raw performance, we would choose this top method. But in fact, there's not that much difference between these systems, like really when it comes to implementing it as a service. And so if I look at the training time here, one thing that really surprised me, I expected knowledge distillation to incur a larger training time because it's a more complex setup. We're training from scratch. But in fact, the dominant factor here was that the transformer-based method was in fact taking much more time. So in fact, it was the architecture of the neural network we choose that has the biggest impact on training time, not just on the usage, but on the training time. So that tells you, choose your neural network carefully, and knowledge distillation is a good thing. So the second part, I'll move on to the embodied emissions. And so this maybe relates to the training because, of course, the training doesn't happen in a vacuum, it happens on a machine. When we talk about embodied emissions, we're usually talking about the extra carbon footprint involved in producing the machines involved. We can also think about e-waste as well, so I'll think about that a little bit. In this context, it comes up because we might choose to do training on a standard cloud data center. We might have our own sensor devices. We might be purchasing new hardware or just using existing hardware. So it can vary a lot. Yeah, and so this is not about training now, but let me give a nice example. There is a very popular device for acoustic monitoring called the Audio Moth, which is a little cheap sensor device that bioacousticians quite like. And we were thinking about the question of, so this doesn't typically run a neural network, but we were thinking, can we run a neural network on this system? It's very low specifications. And the answer for us was, no, we can't. But that's not an inherent limitation, that's our own failure. So we used software libraries which are designed for porting neural networks onto small embedded devices, and there's a lot of progress in this domain. In our context, we didn't manage to get it onto this device, but we got it onto a slightly larger device. And so there's plenty of room for improving on this, and I'll refer back to that slightly later. But the audio moth, right. I'm thinking about global scale, and can we use this at large scale? Like this is a lightweight device, but then again it has a footprint. How many audio moth devices are there actually in the world, and could we use that for global scale monitoring? The number of audio moths that have ever been produced is apparently about 60,000, which is impressive in the world of bioacoustics, but if we want to cover the planet, well, we're not there yet. So we'd like to scale this up without scaling up e-waste. So here's a dedicated device that we could potentially be using for real-time acoustic monitoring. But there's a different device we can use for real-time acoustic monitoring, and it's one you know very well. Okay, so it was already there in the first talk that it's quite common to use citizen science using smartphones in this field. So again, I'm talking to you about something that is not actually very novel. We do a lot of this. I have run this Warbler bird sound recognition app for 10 years. It's UK only, by the way, in case you're wondering. Yeah, it's been running for 10 years. People use it. People are happy. Ops Identify is produced by Naturalis, and that, or at least powered by Naturalis, and that runs for all of Europe, and that's image classifier. Works great, lots of people using it. So again, it's not very novel, but it has a low footprint as a method, because we're using existing sensor hardware. I don't believe that there is a significant number of people buying a new smartphone in order to use these apps. And we're using cloud data servers mostly to handle the data coming in from those things. Now that doesn't have zero cost in terms of impact, but it's typically low. And even if we're scaling up very large, we're still small fry compared to many of the other things happening in data centers. So I think that's good. I think it's a reassuring thing for us in our reliance on this smartphone citizen science. Ashin already mentioned in his talk that one reason we can't rely on that is that we're only monitoring where the people are, and that's a problem. We'd also like to be able to scale it up and go further, and maybe we can take some smart listening devices and leave them in remote locations, but then we still have to think about the footprint of those devices. So maybe we can reuse old hardware. What is the most common old hardware in the world? I've phrased the question quite ambiguously here. Don't worry, I'll give you the answer. I'm thinking about acoustic monitoring, and so I particularly want to think about smartphones, or at least phones. All of these devices are more than 10 years old, and there are millions of them in the world. Well, this adds up to billions. If we can repurpose some fraction of those for acoustic monitoring, I think that would be fabulous. Of course, we still have to take care of the e-waste questions that come from it, but we have these acoustic listening devices ready, and they can probably run slightly more advanced algorithms than the audio moth. So there's a potential there. In fact, there's not just a potential, it's already been tried. This project is a US organization called Rainforest Connection, and they've been doing this for quite a long time as well. So they have this lovely idea. They want to monitor illegal logging in the Amazon rainforest, and they want to do it by putting a smartphone with a solar panel on a tree, and then to send alerts when it detects logging. And they also want to go further than this. So they do want to do nature monitoring, not just detecting logging sounds. And they're working on it. But I think they haven't quite got there in the automatic sensing yet, and that's because it's still quite a big challenge to run these acoustic recognition algorithms on small devices. So I think they had a great idea, and they've been working on it for a while, but I think we can help them, or globally, we can help with these ideas. So this slide is addressed at the computer scientists in the room. Okay, so we're going to design some algorithms for very low-spec devices, right? A horror story here. You don't get a GPU to process your neural networks. You don't even get SIMD on some of them. You might even not have floating point numbers, right? So for some of us, that's terrifying. But it's actually, it's a really interesting domain. Now, I've only really recently got into it, but even on modern devices, these low complexity algorithms can be useful because the device can then also run in a lower power mode, even if it's a modern device. So I think this is a growth area that we should think about. There are lots of ways of doing this. I won't go through this whole list, but there are plenty of tricks of the trade and active research in this. One of the most common things to think about is quantized neural networks, which basically takes a floating point trained deep network and turns it into an integer version. But there's lots of work there. I think there's lots of potential projects for someone. The third part of the talk, I wanted to say a little bit about the energy footprint in use. And so we know that training a deep neural network can be a heavy process, and doing the inference, well, if we're just processing one image, that's very lightweight. But of course, I want to do that billions of times. And so the inference footprint could also be large. Is it larger than the training footprint? Is the training footprint larger? Well, let's see. I return to the idea of knowledge distillation, which was originally introduced, in fact, with the idea of training a small model to replicate the abilities of a large model. So it was actually originally intended to shrink models, and that's very useful. We have applied this in one example of acoustic monitoring, and in this case it's one of the tasks that we need to do in biodiversity, which is detecting human voices, such as those ones. And what you see here on this plot is you can see the floating point operations, so that's how much, how heavy the algorithm is, versus performance on the y-axis. And the good news here is we had the good luck of taking, oops, I've pressed the wrong button again. Taking this the system which already existed, this teacher, and we were able to shrink it into a smaller model and, wow, actually also improve the performance. So it's not just that we didn't decrease performance, we improved it. Now this is something that, of course, occurs in deep learning, and it can be that a smaller, more constrained model is imposing more constraints on the problem, and so that's why it can sometimes be better. In our case, it's good luck, but it's also a good thing to think about. So, now let's put it all together. I want to find a balance between the things that I've spoken about. And just in the final minutes, I will give a worked example, a very famous worked example of GPT, and then I want to compare it against the kind of thing that we do. So, here are some numbers for GPT, and I've visualized them down below. So we have a measuring bar here of 10,000 kilograms of CO2 emissions. The training footprint here, this is a good estimate of the training footprint for one GPT-3. And then typically the embodied emissions corresponding to these things, they've been calculated in various ways. They very often come out as about 20% of the direct footprint. So this little grey bar here, that's the embodied corresponding to the training. And then the inference here, if used 1 billion times, with the embodied corresponding to that. So 1 billion times, when I wrote these slides, 1 billion times was, I think, 2 weeks of using GPT, but now it's used 1 billion times a day. So, in the case of GPT, this green bar is perhaps the overwhelming thing. And so the inference footprint is really important here. So let's compare that to my nature example. So I'm going to do the same thing for our image recognition service, which is a running service at Naturalis. I'll do the same thing. So here's the plot. I want to point out that the measuring bar is much smaller, so it's 100-fold smaller. Our system, of course, it's smaller than GPT. So we have measured these things directly, thanks to Laurens Hogeweg. Oops, I'm pressing the wrong button again. Laurens Hogeweg, who is basically the chief engineer of this system. So this is image classification, which processes 80 million images per year of nature images. The training and the inference are there. I've actually had to scale up this inference. So we run training on our own data servers, and then at inference time, we're actually running it in Sweden, because Sweden has the greenest energy mix. So our inference system runs on cloud servers hosted in Sweden. In order to make this green bar visible at all, I've had to pretend that we're not running it in Sweden. But of course, so the actual electricity source, of course, makes a big difference. I'm not focusing on that. But you see here, this is basically our carbon footprint per year, because we train our system once per year. That's how it's done. And we run, at the moment, 80 million per year. So in our case, the training footprint is the thing to focus on, and that's where maybe we can do some research and refine it. It also takes a long time to train, and so this would be a great thing to improve. We should also add the hardware footprint if we were using a lot of sensing devices. I don't have numbers for that, so I can't show you. But this is approximately what we're aiming for. And of course, if we're going for global scale, we would scale it up. But still, this green bar is not going to overwhelm the training block, at least for now. One of the things I want you to take away from this visualization is that it's actually not a done deal whether it's the training or the inference that is the excessive part of the model here. So basically, we need to work on both of them. The overall implications are efficient training and inference are important. And even if we train a very big model, it's important that we also then train smaller models from it. We should do more of this. And the good news for people who work on algorithms is that we need more of them. We need these efficient integer-only algorithms, for example. And just before I finish, I want to refer to one other aspect, open science. When we're reusing each other's work, that's another way of reducing the footprint of what we do. In that context, I would like to announce that we are launching a challenge, a data challenge called biodiversity. So this relates to the decase challenges in acoustic recognition, which have been running for many years now. And we're very happy this year to have a satellite workshop and a satellite challenge, which focuses on biodiversity detection. So for that, we've got 3 different tasks that you can have a go at, including one to try and do bioacoustics on these tiny hardware that I referred to. So you can help us solve that challenge. So the challenge is open now, fresh data sets for machine learning folk to work on. And the challenge is called biodiversity. So bioacoustic AI monitoring for nature is needed. The good news is that we can tread lightly, and there is work to do. The list of papers that I've spoken about is here, and there is biodiversity. Thank you.
Thank you, Dan. While you think of your questions, I'll just shortly ask, the training time that you report here, is that including the development? Like, do we train the model several times to develop it?
So, no. What I've reported here is the training time for one network. The development time, this is something that can grow and shrink, and it's very hard to put a number on it. But the system that I'm referring to in Naturalis is a system that is in production, and we don't put a large amount of time onto developing new versions of it. It's simply retrained every year. So once a system is in production, there's basically just one training per year. But you're absolutely right that that should also be taken account of.
Thank you.
Thank you. One question I had was, if it's doing cloud processing, what do you do for monitoring areas that don't have necessarily mobile network coverage? Or if you're running it locally, how do you do the collection of the data?
Yeah, good question. A lot of what we do, the devices that we use, many of them, in fact, don't have communications. And so there is with the present technology, there's a limitation on actually gathering the data. The system that I described that is running from Norway down to Spain, that's using the mobile phone 4G network to send the data back. Now, where we don't have 4G data coverage, that's difficult. Yeah, I haven't solved that problem. There was a question at the back, actually.
I think that's related to that one, because I probably missed your explanation, but why do you want to run the models on the devices rather than send the audio recording, which is what these devices were made for in the first place, and then process that on big servers?
Yeah, there's a section that I wasn't able to fit into the time in this talk, which is about the carbon footprint of transmitting data. So if we send the raw audio, actually there are privacy reasons why we might not want to send the raw audio, but if we focus on carbon footprint, sending the raw audio is not optimal because it's a large amount of data. Sending the classification decisions that have been made on device, that could be optimal in that sense. However, I think in practice we want some kind of compromise. We want initial filtering by a relatively smart device, and then we send some pre-digested or partial information back to base. And so actually that's the best balance.
Yeah, thank you for the very interesting talk. I have a question. What is your counterfactual scenario? So the alternative to monitoring with AI is monitoring without AI. And so how do these numbers compare to if we just continue monitoring as we do? I mean, I have to imagine that has an even larger footprint, a massive footprint in some sectors.
That depends on a lot of depends on a lot of things. It's very, very variable. I am in favour of, and at Naturalis we're involved in a lot of classic citizen science, as well as the classic monitoring programs which are centrally organised. So firstly, this doesn't replace those things because we always need some manual monitoring which has different benefits. So we would always put those two things together. If we think about the global south, I think that's perhaps the place where it becomes a question to ask, because we would there are very large geographical scales, and it's also quite difficult to typically there are not the professional networks of monitoring that's really going to cover those scales. So although we can do a lot with citizen science and we can scale it up pretty well, the classical AI-free citizen science, which might involve amateur experts, it's just not easy to scale it that far, I think. I would put it all together, but the carbon footprint of those more traditional methods, it's difficult for me to answer. I mean, if you just have some local experts, well, we have to decide how far they travel, etc. But yeah, I don't know.
All right. So let's thank Dan again.
Thank you.